Okay, so let me start to introduce a bit this event. Welcome, everybody. It has been a long time since our last Pi and AI Darmstadt events, so Space Edition. So we are organizing Pi and AI events, which are basically specialized for space. So what we do is we cover every time some topics about space application. So it could be text mining, autonomous systems, so more like computer visions applications, or sometimes anomaly detection. So some AI application applied to space. And so that's what we try to do. We try also to cover different phases of a space program life cycle. For example, we try also to have speakers to talk about the design process, but also about operation of a spacecraft or rover once it's actually in use. So there are different constraints, both design and operations, and we have always a great speaker to address it. And today we are going to talk about research in space technologies. So, but before we start, before I introduce you to our speaker, I'm really curious to see among the participants, where do you guys come from? Can you tell me which country you are from? I think usually we have a very diverse group of people from all over the world. Okay, so we have UK, Switzerland, UK, Portugal, Latvia, India, wow, amazing, Serbia, Turkey, Nigeria, France. That's amazing. That's quite and Spain, wow, that's really diverse. Germany, great. So I'm also in Germany right now, and I think our speaker is joining also from the UK. Great. Also, another question to all of you guys is whether you can tell us if you are more like an AI guy or girl, or more space professional or students, or maybe you are both. So if you can type in AI, space, or both, this could be great. So we can also see our audience, and our speaker maybe can adjust a bit. So we have AI, space, deep learning, both. Okay, great. More of AI, but love space exploration. That's great. You are on the right place. New one. Yeah, maybe you are new to both of the field, and then you will probably be able to learn a lot. And robotics, love space as well. AI, but want to learn more about space applications. Then, yeah, we will talk about that. So that's amazing. And so I'm taking this opportunity that we interact a bit, that to tell you that it's also the time for you to ask questions. We'll probably do most of the question at the end, but feel free to ask them anyway in the chat, and we'll come back at the end to take a few questions. So don't be shy. So now enough speaking. I think I spoke enough to let the remaining of people to join. So also just one note is that this event is recorded. So if you have to leave earlier, don't worry, you will be able to watch the replay, but it's better for you if you stay, if you want to ask questions, of course. Great. So now the topic of today, I'm super glad and excited to welcome Professor Yang Gao from University of Surrey. She's a professor in space autonomous system and also head of the Star Lab. So I will let her introduce herself, and she's going to talk about AI robotics and the research work she's doing along with a colleague at Star Lab. So welcome, Professor Yang Gao. Welcome on stage.
Thank you, Patrick. Can people hear me okay?
I can hear you.
Excellent. So hello everyone. It's such a great pleasure to be here and joined by all of you to this conversation. As Patrick was alluded to, I'm an academic university professor at University of Surrey in the United Kingdom. I have been a roboticist for over 20 years. In the past 18 years, I've been primarily looking at problem solving for space applications using artificial intelligence and robotics. I also serve a number of community activities, such as being the editor-in-chief of Journal of Field Robotics, which is a QN journal that publish research work or also development work from both academia and industry that look at unstructured environment such as space, and looking at particularly test results so people can see how robotics and AI can be implemented, applied in real world problems. I also had been the mentor for a Space for Women program organized by United Nations, which is really a platform trying to encourage girls and female professionals to take part in the space activity. So it's very exciting initiative. So today, what I really would like to do is to probably first talk myself, but hopefully later we have some time to engage with the audience and look at people's interests and have a bit of a discussion. But it's really, I'm trying to summarize some of my thoughts, ideas, and my experience about how AI robotics has been playing a role in space exploration and exploitation. But what is more important is how these technologies can help support these exciting human activities in a sustainable manner. First, I would like to talk about space robotics, put it in a slightly bigger context. Of course, we hear from the audience there's a mixture of people working on AI, working on space, but also a bit of combination of the both. When it comes to space robotics, I think it has to be recognized that this is a topic that really build on a number of existing scientific domains. So for example, we draw a lot of knowledge from terrestrial robotics, comes to sensing, perception, mobility, locomotion, navigation techniques. Also computer science, that's where AI principally have been developed from. So there's a lot of knowledge there in terms of mission planning, machine learning, and soft computing that space robotics has been built based on. There are also space engineering, which of course is not specific to robotic system in space, but also more generically the spacecraft in general. And that's where that we really be able to congregate knowledge and experience in how to do software, hardware, harness, how to perform spacecraft system engineering, and how to qualify space systems. There are also other subjects such as advanced material, information technology, biomimetics, that space robots has also taken advantage of. There's also interesting point to note that a lot of design drivers, requirements, and specifications that space roboticist has to build a design around is coming from space science, because a lot of space robotic system has been tasked to perform scientific missions. So a lot of requirements for space robots come from that direction. It's also worth highlighting the fact there are emerging domains that space robots can help develop, such as in relation to space law, space architecture, space tourism, that the form of capabilities that robotic system can deliver is very relevant. I think it's been very well known that existing space missions has already flown artificial intelligence and robotics. So for instance, around the orbit, Earth's orbit, you have robots in the LEO, such as International Space Station, in the form of robotic arms that have been supporting astronauts' operation on a daily basis. You have the robots in the GEO, for example, to help deploy antennas, solar panels, and you have obviously the interplanetary missions where you have rovers on Mars, the Moon, as well as small bodies. This table here is trying to summarize as much as I can the successfully flown robots around the Earth's orbit and interplanetary. Well, this is in no means a full list of the robots that has been launched, because that list would probably be twice or 3 times longer than this. But not all those launched space robots has been very lucky and successful. So these are probably the lucky ones. What is very interesting to note, first of all, is the time frame. So the first space robot, in terms of being an assembler, has been very successful in the 1960s mission to the moon by the US. And then subsequently, you have more diversified form of robots that's been successfully launched and operated in missions to the moon and beyond the moon, like the Martian surface, asteroids, comets. And you can see the diversification of robots in terms of locomotions. So you have surface mobile vehicle, you have manipulators, you have assembling tools, you have drilling devices that go into the regulars, and you have quite recently the Mars mission 2020 that has had a flyer, a helicopter vehicle, which is quite exciting. Of course, there's a diversification of the international players that has been made this mission successful. It's extraordinary achievements across the globe. Looking into the future, you certainly can see a growing demand for AI and robotics into future missions. For example, you like infrastructures to be constructed, for example, in orbit, such as the Large Space Telescope that can be self-assembled using robotics and AI. You want a robotic satellite that can go and grasp and retrieve space debris. You want robots that work as a team with human astronauts, or even human-like robots in space and more autonomous explorers in space. There are two, I think, fundamental capabilities of robotic system. One is in terms of its mobility and locomotion. So what we're saying in terms of long-term development is really the diversification of the mobility for future spacecraft. So you would like to have robotic platforms that on land surface or even water surface. You want the aerial vehicle, of course, provided that that particular space environment has air to fly things. And then you want subsurface robots, in terms of drilling in different forms, and even potentially submarine. And there's also manipulation in terms of multi-degree of freedom, arms, fingers, hand, and sampling tools. Another key attributes of robotic system is really about its onboard autonomy. So this is directly related to artificial intelligence. Based on the ECSS standard, there are 4 levels of autonomy on board spacecraft. So starting with teleoperation, move to automation, semi-autonomous operation, full autonomy. So if you look at this particular figures trying to classify existing spacecraft in terms of level of autonomy on board. So it's not very surprising that the early days, the space vehicles or robots tend to be lower in the autonomy. So you're typically looking at teleoperation, particularly with those lunar vehicles, and some of them might have automation on board. So this means all the command has been pre-programmed, embedded in the onboard computer. A large range of operations, robotic operations in the ISS has been teleoperated by the astronauts. And of course, you're seeing a growing capability in the onboard autonomy for space vehicle, particularly reflected by those surface rovers in the Mars or lunar missions. Looking over the horizon into the future, I think we're looking at more and more fully autonomous space vehicles and robots, either it's on surface or in air. And you're also looking at increasing capabilities of space robot in the form of a shared autonomy between the machine and the astronauts in space.
I think what you're mentioning right here is quite interesting, because quite often we can see a very animated debates about robot versus human exploration. Why should we do human exploration or just robot? And I think the way you phrase it, that robots and humans should work as a team, so to find synergy. I think that's really interesting and should be put forward even more.
Sure. Yeah, I think definitely. I think I agree. Sometimes the debate can be a little bit too limited in terms of maybe due to prejudice, and sometimes people think it has to be some kind of competition between the two. But I think in the long term, what we're really looking at is ecosystem. That ecosystem has to include a human in the loop, has to have those very powerful capabilities by the machine. So I completely agree with that print. And particularly this table might help to go into the more technical level, if you like, of space robotic system, where we try to break down them into some of the key areas that help people appreciate the key technical challenges and needs. I think there's sensing perception, there's mobility, which was highlighted earlier. There's also level autonomy that was also explained from the sort of historical perspective, and there's human-robot interaction. Again, I think this is going to be more and more important as we see more infrastructures being put in place in space, where human can have a longer period of stay in space. So I think this kind of interaction is very important. Not forgetting system engineering is always this overarching area. I think it's very important that we never forget that, you know, when we develop machines that is probably becoming more and more intelligent and autonomous, verification and validation of such machines is critical. We need to be very wary of the safety and trustworthiness of using these machines, particularly in a very remote scenario. So my next slide in the talk, I try to break things down into two kind of mission conditions and start talking about the opportunities you know, moving forward, as well as some examples of technologies that have been developed, particularly from my team, just as examples. Of course, there are a lot of other techs being developed all over the world, but just give colleagues and audience in this room some examples, some tangible examples. So I first like to look at the orbital scenario. So these are missions that principally around the Earth, our own planet. And it is believed that there will be many on-orbit applications that require advanced AI robotics in a time frame of 2025 and 2035. And these missions could range from the clean space or space debris removal to on-orbit assembly, servicing, constellation for mission flying, etc., etc. But from the technical point of view, what I want to talk about here is that even they're all around Earth's orbit, there's still differences in how the AI robotics might need to play a part. For example, you could be dealing with cooperative targets or non-cooperative targets. So typically the cooperative targets are things that you have communication links with. For example, you have quite a good knowledge about. Well, non-cooperative target typically refer to things that you have limited information, or even sometimes maybe, you know, no prior information, and there's certainly no communication means with it. And there are also differences in where you actually deploy your robots from in terms of its base unit, its base platform. So you could be deploying it from a pseudo-fixed platform, such as the ISS, or free-flying, such as a small satellite. So all these differences in terms of mission scenario can really make a big difference in how and your robotic system have to perform and what are the key challenges. So this sometimes would introduce different requirements, you know, when you design robotic system using artificial intelligence, for example. The first project work I would like to use as example is something we did under a European Space Agency project, and this is actually a mission called Purpose 3, and this is a mission that meant to launch 2 spacecraft to help study the solar corona, and the 2 spacecraft will also help to demonstrate some formation flying technology. So there's an onboard instrument called Fan lateral and longitudinal system, and this is an instrument that is developed based on laser to help measure relative attitude between the 2 spacecraft, and it has been given a very demanding task, that is to achieve a high accuracy of 300 micron at a distance of 250 meters between the 2 spacecraft. So you can appreciate this is a mission that use 1 satellite to look at the sun, where your other satellite sits in between of the observing satellite and the sun, which carry a round plate. So you want to put the plate, in the middle of the sun, so that the observing satellite can just look at the corona. So that's very interesting experiment. So here there's some very interesting challenge we took part in industry consulting to help resolve. That's to do with the calibration of the laser instrument. So when it's measuring the relative attitude, I think the lateral motion is in particularly very sensitive to any small movement. So here there's some very cool ideas we put in place based on machine learning to help look at the data and develop this offline calibration tool. And another example of what's relevant here is look at relative navigation of spacecraft for in-orbit servicing and assembly. So here, in terms of research, we've been given challenges to only use a monocular vision for post-estimation or relative navigation between your servicing satellite and your target, your servicing target in orbit. So here, the key, I think that the key novelty, if you like, in our development is using convolutional neural net and train it offline, pick up some of the data. For example, you can see from the tools we developed to use those data set as a training for the neural net, and there's a deep learning methodology involved. And after that, you can use the CNN for online estimation of the pose. Of course, there are also some online solutions you have to introduce so that the method is adaptive to anything that maybe your training data set couldn't completely capture. So just to also put that into a end-to-end demo, you can see we could potentially use this sort of technique for autonomous docking with a space mirror segment. So in the film that is played here, you can see that on the left-hand side, that's your servicing arm carrying a docking part. On the right-hand side, that is your mirror segment. So they are part of the segment that carry a small piece of mirror. So the task here in orbit is to autonomously rendezvous and dock. So this video also only shows a docking phase, approaching docking phase. So presumably the rendezvous has been completed. So you can see that from the visual camera on board the servicing arm, you can see that target piece in space. And what is very interesting is really that last bit where you can see that the target is probably already lost, is already, your field of view has lost that target for a few seconds, but because of the machine learning technique we have applied, it still be able to successfully dock with the target. Another interesting application around the orbital challenges is to do with the grasping, manipulation grasping of non-covered targets. So when you don't have a great deal of knowledge of the target, what you need to do is to autonomously go and manipulate and grasp. Here, again, our technique is a bit unique. It uses very sparse point clouds for the sensing. So just play the video on the top right-hand side of the slides. You can see, when you are finished your rendezvous, the arm on the satellite need to go and first detect and grasp a debris. In this case, is a nozzle of the span motor. Well, the thing is tested on the hardware in the loop system, which perform exactly the same way as what's in the simulation. So basically, the technique, again, using the visual cues to help identify the suitable surface point to grasp. So in this case, you can appreciate this is only a two-fingered gripper, which is probably the most less complex and less costly gripper that's possible in this case, and with only two contact points that we were able to quite successfully detect the suitable grasping surface and retrieve the debris. Well, moving on, I would like to next talk about another key group of space missions. This is dealing with interplanetary surfaces or extraterrestrial body surfaces. And there are also a lot of missions that has been planned. I think a lot of them is already under development. A lot of them are maybe being in discussion. This also covers quite a wide range of mission objectives. For example, the sample return missions. And we already know, for instance, the Chinese Space Agency has its second lunar sample return mission to the moon, and the second time it could be from the far side. So that would be very exciting. And then there's also the Mars sample return mission, which is likely to be a joint venture between ESA and NASA. So those sample return missions typically involve sample fetch rover that need to explore unstructured terrain and collecting samples from surface or subsurface. If you're looking at beyond 2030s, you could be talking about missions that want to do manufacturing assembly, ISRU, particularly on the moon. And you have the ESA's Moon Village initiative. You have some joint plans between the Chinese and Russian space agencies about this International Lunar Research Station. And we also know there are a lot of commercial initiatives to exploit the moon or even small bodies in terms of mining, in situ resource utilization. And from the robotics point of view, I think we need to really offer solutions that is more in the form of more heterogeneous robotic systems to help build infrastructures. Going back to what being said earlier, that ecosystem between astronauts and robots, particularly if people are serious about setting up a kind of outpost or permanent habitation around the south pole of the moon. So similarly, just to give you a few examples about technologies being developed, and particularly from my research group and in collaboration sometimes with industry. One example is really help supporting sampling. And here, this is the example of how to use a vision guided system to achieve high accuracy placement for robotic arms. So here, for example, with some return missions, very often that could be requirements from the science group to say, I really are interested in a particular type of rock for you to take samples, or there's a particular part of the rock I really want you to place the arm. And so that the end effector of the arm can collect the sample at a high precision accuracy, so that the scientific goal is met. So therefore, the robotics designs has to really help, achieve that. And here, the solution we come up with is saliency-based, which allows relatively more robust feature tracking. Because as you can appreciate, when the task is about collecting samples from a rock, and very often you're looking at a visual thing that is very homogeneous, that's really difficult to differentiate and track. And when you are a bit distant from the target, you still have, you have those boundary areas that can help really orientate. But when you start to get very close into the rock, that's where things get really challenging. So here, what AI can help is to produce that extra layer of capability and give you that good trade-off capability between the detection accuracy and precision and potential computational load, meaning maybe onboard computer is not going to be able to cope with that. So there's a very good trade-off layer can be achieved and managed by AI. So this has quite a good application to those future missions, such as sample return. There are also some very interesting work we did in terms of processing big data, particularly visual data, image data. And this is a project that was very interesting, where we were collaborating with some scientists in Chinese Academy of Sciences who get this huge volume of image data from their lunar missions. And these are very high quality resolution image data. This was a mission, I think one of their early lunar landing missions, not the most recent one, but the early ones, where the rover, I think, had some problem with one of their mechanical control units. So it kind of couldn't move after traveling, I think, about 150 meters or 200 meters from the landing site. But it had this rich amount of data. So what we managed to do, we come up with this very innovative idea. So we took their high-res image data and combined that with what we call thermomechanics models. So we perform a deep analysis of the image, and really looked into the sinkage of the whale and looked at the behaviors of the whale traveling on the soil from that landing site. And we used the same methodology and applied it to data from the Luna 17 and Apollo 15 landing site. We did a comparison of this landing sites in terms of soil strengths or soil properties, and which was pretty interesting, because considering the fact, none of this mission really carried dedicated instrument to measure the soil stiffness, but with the visual processing and combining with thermomechanics, we were able to actually come up with some understanding of the soil properties. So that was quite interesting results. I understand, the team there has also used some information in the future missions. Another example of robotics project is our work in the sort of ESA's ExoMars rover mission. As we know, ExoMars rover mission was the second part of the ExoMars mission, and which I think is supposed to get launched this year. And I think there's some delay in the launch. But what we were doing there is we're partners in the team that looked at the development of the science instrument, which is called PanCam. So this is a science payload meant to be used to characterize the biological environment on Mars, which is quite important scientific investigation. But we're part of that team to help develop a framework that really allow us to maximize the use of the data from the camera. So we developed this framework that really help put together the different sensing data and create a GIS system that can really help allow the information coming from the instrument to not just service the goal of the science team, but also the engineering team. So meaning the GIS system will help guide the scientific team to say, oh, how I want the next science target to be for the rover, but also for the engineering team to help navigate the rover in a very safe and productive way. Moving to next few examples. So far, you probably noticed we've been mostly talking about a lot of software development, navigation algorithms, sensing, perception. But I did highlight the fact that the locomotion system or mobility is actually very critical. For example, here is an example of the work we did to help enhance the surface mobility for future rovers, and particularly to make future rovers as compact as possible. Because if you think about those sample return missions, you can appreciate the fact that, if we can make those rovers smaller, more compact, and more mobile and capable, then we can potentially launch more than one of them. And that could significantly increase the mission productivity. So here is an example. We draw inspiration from biological system, where we developed active suspension system, which only use 2 linear motors. We're able to demonstrate both crawling behaviors and climbing behaviors. So you can see that it's a micro rover design, only 4 wheels, which is and with two added actuators, the chassis could perform this crawling behavior that which is shown on the left hand side, and then this climbing behavior. So just put things into perspective. If people are familiar with robotic design, which is a passive suspension system and used widely and successfully with with Martian rovers by NASA, that was a 6-well platform which doesn't have active suspension, but it's very capable. It had, I think we try to devise something here to improve that crossing capability over a wider range of terrains. So for example, the video I'm going to show here shows you the actual tests. So first of all, on the left bottom side, it shows how the crawling behavior can successfully save the rover from entrapment into loose sand. Okay. And then the next film on the bottom right-hand side, showing the same platform, but in this case, it's highlighting the climbing behavior. As you can see, the rock is actually at a height more than twice of the radius of the rover's well, which is quite extraordinary, actually, in terms of its capability. Another very important example of locomotion is about subsurface locomotion, because stumbling is into the subsurface and regolith is actually quite important. So here again, we are drawing inspiration from biological system. Here is the design we've been leading and developing for quite a number of years. It's a drill called WASP because it was inspired by the ovipositor of wood wasp, which use what we call dual reciprocation drilling mechanism. So you have two halves that goes reciprocatingly, and the penetration was largely achieved by the traction between the drill and regolith. So this sort of animation shows actual numerical simulation of the drill motion and its regolith particles around. And this was also developed and tested in hardware. So that's played in the next film. Oops. So you can see here that the reciprocation was quite effective in drilling into sand particles or regolith that was granular particles. And also people are interested in taking samples while you are drilling. So here we also are able to show that how we design the sampling while the reciprocation is taking place. So again, similarly, we have hardware tests. Oh, sorry about that. Sorry about the bottom right-hand side of film there. That sort of got distorted. I don't know why, but it seems to get distorted. Sorry about that, but I hope you can still see things moving because you can see quite clearly.
Yeah, we can see the
yeah.
moving, yeah.
I think it's an editorial problem there. But just to give you your idea how this kind of mechanism development is also really important. Another thing, just to mention, which often get overlooked, is that a lot of work we are developing in the robotics field, particularly if it's in a interplanetary environment, very often we need to deal with robot-soil interaction. So this could be that through the wheels or tracks or legs of your mobile robots or your drilling devices or your assembler. So that's very important that we have techniques or knowledge to develop those simulants, those regular simulants. And it could be either in digital form or in physical form. So for example, here, there's some pictures showing some of the soil simulants that we developed for Mars soil as well as for lunar simulants. Some of them are icy as well because it's in the south pole of the moon, and we believe there are icy water in the regulars. So those regulars are quite special. Digitally, there are also methods such as discrete element methods that help us simulate the regulars. So, for example, we can use DM to help simulate how the whale might interact with some of the soil in the surface. And also, you can do that also with the drilling device as well. So you can see, in this case, we just use high-performing computers help you really establish some of the behavioral conditions between your robot and the regulars. And it's quite useful to help characterize things and perform trade-offs before you actually constructing anything in hardware, because the latter is obviously quite expensive and time-consuming to do, relatively speaking. I think towards the end of my talk, I really want to add a few words about the future, looking into the future. What I think are things still open issue that need to be further investigated. There has to be more effort in research or development. But the key goal, in my view, is really about making space operations more sustainable. I think that the sustainability is really the key word here. So in the near midterm, I think there's still quite a number of outstanding topics or areas for technologies that need to be further developed, particularly around low computational, high accuracy mapping and perception in the 3D space. Also, energy optimized locomotion mechanism and control. Resource aware computation. Particularly when you're looking at introducing more AI or machine learning, you would naturally face issues such as parameter tuning. There will be more parameters to be tuned. Maybe somehow has to be done heuristically. So that's something very important we bear in mind. There's also reconfigurability, self-verification in runtime, in real time, for both hardware and software. I think that's very important. There's a lot to be done there. In the long term, it's really about making future generation spacecraft long-lived, very robust in mobility, but also more autonomous in terms of its capabilities. For example, one of the things I thought should really be looked at more and more is to move from weak AI to strong AI. So because at the moment, I think most of our design practice is still adding AI as afterthought. Okay, once you develop the spacecraft, space rover in a traditional way, you try to add more capabilities. So very often AI is a tool to do that. But this is really quite weak in terms of the level of intelligence. I think moving to strong AI really means that you develop the system bottom up with embedding AI from the very beginning, such as the software architecture, the very fundamental software architecture to be domain independent, more generic and reusable. It can incorporate reconfigurability. It's almost like embedded in its DNA of the system. So here, for example, what I'm showing is just a small example. We have done previously, we can switch between different software packages in real time inside the software system, and that can be also be a hardware, a piece of hardware as well. So this is really enabling AI at a very fun level. I think that's quite important moving forward. I think just to give people some, if you're interested in some of the things I talked about, there's a new book which was launched beginning of this year that summarized some of the stuff that was done, not just by my team, but some other contributors around the world. I think it's something, if you're interested, you can pick it up. Yeah, I think that's my last slide. I will probably pause and so that there's a bit of a opportunity for audience to ask some questions.
Yeah, thank you very much. Yeah, we have some questions. I also have questions, so I think we can stay a bit more indeed. So yeah, thank you for this overview. I think it's really impressive to see the diversity of applications and topic, and also interesting to see all the burning topics and the gaps that still remain to be filled. So thanks for that. Okay, so we have one question. Can you just say the name of the book again, please?
Sure, yeah. Let me just, can you still see my slide? Yeah, so this is the, yeah. This is a more recent one. I do have another one which is on the planetary robotics, which I will probably put in the chat if people are interested too. So this one is sort of covers both orbital and planetary, and it's most recent. So I thought it might be useful. I will also put it in the chat so people can, if you haven't captured or note down, I will put it in the chat. Yeah. Okay.
Yeah. Great. Thanks. Okay. So if you guys have some questions, it's also an exciting part. So feel free to ask. So we have a few of them. Let's start with one. What methods or how do you integrate AI into space exploration locally? So I'm not really sure what do you mean by locally? Maybe on the device itself. That's what was meant in the question.
Yes. Yeah. If Kali can clarify the question, what method do AI into space locally? Yeah. If the Kali could clarify that. Yeah.
Yeah. In the meantime, he's also asking what aspect of AI is most proficiently used in the space industry. So maybe what kind of application, whether it's more like computer vision or.
Yeah, sure. I think I know, for example, there has been a lot of software flown on past or existing spacecraft already using techniques that does autonomous planning, mission planning, for example, scheduling planning. So this has been already used for quite a while. What is coming up more and more is indeed around machine vision. So computer vision, their growing interest in terms of using things like saying and deep learning, GAN, because they're really work quite effectively with volumetric data. So it's a very interesting, promising techniques. I think this is really coming up. There has been also in the past a lot of data processing techniques, automation of data processing for the ground. So for example, when you have data being collected, but you might process them automatically on ground. So there already been some methods being used there. Very often when people think about AI, they automatically think it's just a software, isn't it? Naturally, because that's what we very much think. But I always felt that anything that is biologically inspired, I feel there is a sort of AI element in it, because anything we inspire from biological system that has been evolved through their development, through their lifetime, I think we could say it's some kind of some form of AI. So I thought some of the embodiment system, such as the mechanisms I show, how we inspire biological system in terms of how they perform the locomotion very effectively in energy consumption, in volumes, in sort of in the mass as well, the lightweight. So how they were able to achieve that in a way is also, I feel, is quite intelligent. It's also very intelligent. So it's not just a software, if you ask me. Yeah.
Yes, sorry, I was muted. Yeah, one of the questions has been clarified. So what method or how do you integrate AI into space exploration locally, which means not really in a company?
Sorry, I'm not.
Or maybe what are the kind of tools that you use in your groups? What kind of technologies in terms of AI?
Oh, do you mean how do we program it, or no?
Yeah, I'm not really sure to understand the question, to be fair.
I'm sorry, I'm not very sure about. Yeah, I'm not entirely sure. Do you mean what sort of development tool, such as software tool, or is that the question?
Yeah, possibly we can. Yeah, if you can address that.
I mean, our development, either in space is there is quite a good development process. So typically you have different phases in space missions. So phase 0, A, B, C, D, according to ESA's protocol. Other space agencies might use slightly different terminology, but it's very similar. So at different stages of the development, you go through the concept approval, and then you have the preliminary design, then critical design review, and then breadboarding, validation, So different stages really involve different development tools. As universities, we tend to only take part in the early stage of those missions, as you probably would appreciate, because most of the missions, when it's closer to the launch, is really should be led by industry, because they have to do the communication, validation, and launch integration, things like that. So for university, when we got involved, it typically to the early stage of the mission, and that's where we can use some of the standard research tool to develop, because they're just for early stage prototype. Because the industry will take it to a next level, and they will probably use industrial rated tools to further the TRL. Yeah. So I mean, typically we, in the software side, we typically use C, Python. Sometimes occasionally MATLAB, we use ROS sometimes for the integration work. There's some question asking about gazebo. Yeah,
indeed.
Sure. I mean, ROS, Arvis, gazebo, they're all compatible. We can use them for quick validation, proof of concept, quick demo, integration. And then typically in my lab, we tend to take it a step further into the hardware in the loop tests. So we have some test bed, we call test bed. So the hardware in the loop test bed, we will test them there. And then typically we can probably reach TRL, I would say 4, maximum 5, I would say typically 4 and 5. And then maybe we'll just hand over to industry, we'll take that to 7, 8, 9.
Yeah.
So that's typically what happens. But of course, university can also have our own missions, which tend to be missions that are lower costs, maybe really for demo, they don't have a very long lifetime, they don't have a commercial impact, as such. But that's also possible if there are opportunities. So that means you could potentially have in-orbit demonstration of the technique, which of course would be great. But those opportunities are not as often as you want it to be. They tend to be rare because they do cost at least some millions.
Indeed. So if we go back to the question about the software, indeed, so you mentioned Gazebo, ROS, any other things that come to your mind that maybe the people can look at when it comes to robots simulation?
Yes, I mean, people definitely use ROS. I know even the space sector, they start to use ROS too, which is the sort of ROS industry version. So I know some space companies also use ROS too. In the research lab, we can use ROS, which is not quite handy. It's quite a good integrator. It's like a middleware, so we can plug things in quite quickly, even though it's not very optimized. But it's okay for concept, for validation. Because sometimes it's interesting that when you develop something which is contributing to a bigger system, let's say this particular software package you're developing for a bigger system, the requirement for the local test is, it can be managed quite relatively easily, because you can just set parameters around it. And but it's really that integrated test I find more challenging to do, and that does require team effort. I don't think an individual group typically does that. It's really a consortium, has to really put effort together, and sometimes it really has to rely on some of the big primes, big organizations to do those integrated testing. Yeah.
And I think also this makes a very good transition to our next question from Juan. He's asking, one of the limitations of AI in space application is the lack of training data. This we know every time we want to start some application, we are asking, okay, when it's data driven, where can I find some data? Thus the need for computer simulated data. This creates domain gaps that may make the AI unreliable when deployed in a real space mission. What is your view about this issue? What could be potential solution? yeah, I think that's a real challenge. It's really the gap between simulation to reality.
I think it's an excellent question because it's an ongoing problem. So for example, one of the things we did trying to help is we actually developed what we call photorealistic simulator for generating orbital data sets. So we used the Unreal Engine, things like that. So there are a lot of things from the, I think, computer vision domain you can really take advantage of like, because it's quite a rich domain. There are a lot of development there. For example, gaming industry, we develop a lot of products there. So I think space needs to leverage on those. I don't think space should try to reinvent the wheel or try to do something ourselves. I think going back to one of my early slides, we really should recognize we build on a lot of existing domain knowledge. And particularly, I saw the gaming industry, because they have so much money, they can develop so much new tools for visualization. There are a lot of things in VR, right? Virtual reality, augmented reality. There's so much there that we can leverage. I really encourage the space age to draw, just learn from that and take some of the stuff in for our purpose. Also, I'm more optimistic about synthetic data set because we've been through the development with, I don't know if colleagues do remember one of my slides. I have a film which was actually a film that I can reshare that just in case it's interesting. So it's a very interesting example. I think this one here. So this is a slide. Can people see it still?
Yeah.
Yes, yeah, so playing a film here. So this is actually a screenshot. Not just a screenshot. It's actually on left hand side is the footage from a NASA mission. So it is a real mission data set. But on the right hand side is the rendered data set from our simulator. So we developed using Unreal Engine 4. And you can see the vibration being incorporated there to just make it more challenging as a data set. But can you see it's quite photorealistic, isn't it? Not bad at all.
Yeah, indeed.
So on the right hand side, it is what we did using our simulator, and the left hand side is a real mission data. So what I'm saying is, I'm quite optimistic about having this synthetic simulators. This simulator. I think it should be one of the key tools for the space sector or community. I also encourage the community to have benchmark data sets. So I know at the moment, for example, ISRU made some effort of creating some data sets for, let's say, the orbital pulse estimation, like the speed data set. Of course, there are a lot of limitations of using real world data set because they have to come from a real mission. Sometimes the ground truth is actually quite hard for the mission to get, right? So, but with synthetic data set from those photorealistic simulators, you will find it's actually really good, really useful, because you can play with so many things and parameters, the lighting, the orbit, and you can introduce artificially some of the key problems that you know you're going to face in the real world. And then the biggest advantage is you can get a ground truth so reliably from your simulator. well, with real mission data set, it's even not that straightforward sometimes. So I think we need both, but I'm quite optimistic about having those more and more photorealistic simulators. I'm quite optimistic about them being useful and being actually quite reliable tool.
Yeah. Yeah, indeed, that's a very fair point also to highlight that even though the simulator may have some flow, actually the ground through of a real mission has potentially also some flow that maybe we underestimate. So that's indeed a very fair point to raise. I also had one question, and indeed that answer to the follow-up question, which was could Unreal Engine 5 be used? So yes, I think
Yes.
you mentioned Unreal
Yeah,
Engine 4.
that's fine.
So indeed,
Yeah, we maybe someone from the gaming industry can create a space game that we could
yeah. What I would potentially miss a bit, but this I don't know too much, is so that's really great for the for visual data generation. I'm wondering to which extent such simulator might be high fidelity when it comes to soil or terrain wheel interaction. I think this is probably simplified in games, and maybe here there is some gap to fill as well. So
it is. It again is very relevant, but it's very challenging because I think if you just look at visual cues when it comes to terrain and involve those soil material, it is very hard. That's why in the numerical simulation we go through DEM because they model the physics. So it's not just a visual information; it's actually the physics. But I think combining the two is very difficult. It's very hard. It's possible. I think it's scientifically it's possible, but it's just what is the incentive for someone to invest in this and do it and still get the benefit of return, I think is a question. Because when it comes to the terrain, because the terrain which not like in orbit is mostly just a visual cue you want to approach and that's it. But with the terrain, you not only have the remote sensing in terms of visual cue, but you're going to drive on it. So there will be a direct interaction. So there's a physical model that has to be included. Is quite difficult. That's why people find a lot of us finding, and maybe it's much easier that you just go to a analog site to do a field trial in a desert or
yeah,
ditch. Because it is very hard, and I think unless you have a huge incentive to develop a tool, maybe again someone maybe in the gaming industry, if they can get a lot of money by developing a game on that, then maybe they have an incentive to develop it. Otherwise, I think if it's purely from the space community, I don't think there's enough incentive to develop something that complex. Well, the application of it is actually very limited. It's just space mission. How many mission? With orbital, we can maybe right now argue, oh, there will be a lot of mission going to Earth's orbit because of those commercial interests, right? For servicing, for space debris removal. But if it's going to Mars or the moon, I mean, you can imagine how expensive that is. I think maybe going to moon, commercial mining, maybe there's incentive there. But still, I mean, I think we're still talking about decades ahead, to be honest.
yeah, it's very hard indeed.
I mean,
Very hard.
at the end of the day, it is whether you get enough financial return investment for some of this tech to be developed, Otherwise, I would say focus on what matters to space and then leverage as much as we can from the terrestrial developments because they have a lot more funding, I think, right now.
Yeah. Maybe also to complement on this topic of going from simulation to reality. I also remember that sometimes one practice that engineer does, for example, when they are building simulation in the development phase, they tend to also indeed test it on a test bench that is also different, yes, from space. But then instead of, so they run simulation both for space and simulation configure as the test bench. So in the simulators, they kind of reproduce the actual test bench and then can detect flaws in the simulator with respect to the test bench, and therefore improve the simulator to hopefully fit a bit closer to the actual space later on. So it corrects some flaws of simulator, maybe not everything, but it gets a bit closer.
Yeah, I agree. There should be some cross calibration. I think there should be some cross calibration between different tools. But anything we test on ground, there's always a risk of missing things because I think it's just we have really limited data from space. The training we can get from those past experience, it's very limited. I think it's something I think worth looking at. If there's some synthetic simulator that can run over a long period of time, and there can be some cross calibration with real world data sets. It's just down to someone has to lead it. Someone has to have that drive, drive enough to lead that kind of major work. It's a huge effort.
Indeed. So I have one last question, I think, before we wrap it up, which is about, and I think you mentioned it, we have to rely a bit on what's already developed on Earth. And I'm sure everybody in the chat is aware of the different kind of Earth autonomous systems, such as like self-driving vehicles and so on. So it's very impressive to see the advancement in self-driving car autonomous system on Earth. But I've also heard an argument of someone saying, on Earth we are about to reach full autonomy in high-density traffic cities. There is much less traffic on the Moon or on Mars, so therefore it should be easy. I think it's a bit of a simplification, but I'm curious to hear your thought about why is there such a gap about a car driving in a big city with so much a very highly dynamic environment around, where we already reach almost a full autonomy, whereas on Mars so far, despite all the amazing progress, but still we are not at that level where rocks around are usually not moving.
I think there are probably two key issues. One is that the terrain condition on Mars is far more unknown and diverse than the road condition, because I think on the road you probably can model everything very accurately. You know exactly where the lane is. You know the expectation of people's behaviors. How the vehicles behavior. So we typically call them a structured environment. So it's structured.
Okay.
Mars is definitely unstructured. I mean, the terrain is unknown, but because it's very varying. It's a varying terrain. Some places look very rugged. Some places flat, but some places has loose sand. For example, they have something called dual crust. It's a geological feature on Mars, which look very flat and very safe, but but it has actually loose sand beneath the crust, so things can sink in when it's dry on it. So in those diversification, terrain property, those unknowns are really very challenging. We're still building some database about the terrain. As you can appreciate, it requires a lot of more missions to help us complete the understanding. So that's one thing. Another thing is to do with onboard processing capability, I think, and also this hardware that the autonomous vehicle can have easily. Well, a Mars rover probably can't, is because the Earth vehicle, is not restricted so much by the onboard computation, because everything is in a relatively innocent Earth atmosphere. There's no radiation. You don't need to, get everything really, harnessed. So you don't have that sort of constraints on the hardware at all. You can run, very fast processors on board a vehicle on Earth. Well, with Mars, because of the space environment, those environmental constraints, so we can't have hardware that is as computational powerful, right, as the ones on the driverless cars on Earth. I suppose you can, but they're going to be way too expensive, because to take all the state-of-the-art consumer electronics on Earth, take that through the space qualification, it is an expensive process. So a lot of processors are still probably a few hundred megahertz, that sort of computational capability. To run that, to run even just a stereo vision or some of the laser scanning is going to be very, very difficult. And then not to mention those very complicated algorithm. I mean, with driverless car, you can have your laser scanners, packed around your vehicle, but you can't have, it's way too expensive to get those things go through process and make them space flight hardware. That process is very long, is also expensive. So I'm afraid we don't have the competing hardware. And it also is super unstructured environment. So the two are very not comparable. There's another thing, actually, environmental. I mentioned environmental, but actually there's another environmental issue. Is they face different challenges, because with the terrestrial application, you have a structured environment, but you have also a lot of moving objects, right? You have a lot of landmarks. You can recognize them. You can build libraries about them. But in the space, what we typically have is you don't have a lot of templates. You don't have a existing database to compare with. You have a lot of, sometimes the environment is very homogeneous. Like if you put a human in the desert or in open space, it can easily mess up the human brain, because you tend to get lost. You lost your orientation easily because everywhere looks the same. And there's very rare artificial landmarks.
Okay, yeah, that's a very interesting point
So
as well.
those differences really introduce different challenges.
Yeah, great. Thank you for this very nice analysis. So I would like to thank you very much for your presentation and this very interesting discussion. I think we ran a bit over time, but it was so great to hear your insight. Maybe one final word. Do you have any advice for people? I see someone is asking for people that are interested to get into AI for space robotics?
Sure. So I think people are very welcome to join the family. So first of all, I think it depends if you're studying right now. I think you might want to build your foundation. I think because the space AI robotic for space is still, I think, ongoing, emerging thing. So I think if you're studying, you could pick up AI, robotics, or space. I think try to build a firm foundation, but also maybe a relatively wide foundation as well. Then when you move up, either in terms of your qualification or in terms of your career development, I think you can slowly to maybe get more hands-on opportunities and see where you want to specialize. Yeah. Because I see a lot of, in fact, I recently going through some interviews, so I see a lot of industry space companies start having posts like AI engineers, which is quite good. AI software engineer, which is very, to me, it's such a great thing to say. Is that I think there's this recognition of they want more AI and robotics into the space area. But if you look at the training qualifications, of course, people can do PhDs in such topics. But for undergrad and master, and maybe some masters, I think some master programs in space engineering also start to introduce AI robotics. But for the undergrad, maybe it's not yet. I think you're still talking about more classical, kind of aeronautical, astronautical training program. But I think because it's relatively, I wouldn't say it's new, but it's kind of still ongoing. It's still continuously emerging. So I think the best thing is to try to develop, your knowledge either through some courses, could be even professional short course training, and try to broaden the foundation, and then through some work opportunity, hands-on opportunity, you start to say, oh, how this actually look like in reality if I'm working on it, right? Is that just as exciting as it sounds, or is that maybe a bit, too analytical for me? So I think then you can decide, okay, I might be able to do this. Then you can then find a clear direction, specialize. And that's probably what could work.
Great. Yeah, indeed. Very good final words, I would say. Yes, amazing. So thank you very much for your talk and this great discussion. Thank you everyone who has joined for your questions. It was really interactive, and yeah, I think we all appreciate that. So yeah, thank you very much. We hope to schedule one of our next events soon, maybe towards the end of August. We'll still have one. So yeah, thank you very much again, and I'm looking forward to follow your work.
Bye bye. Bye everyone.
Bye bye.